So, welcome to week 6 and the second lecture, and really the last formal lecture that we're going to do in this course. And what we want to do in this one is use this last topic as a kind of excuse to do a bit of an overview and maybe to point out something that's a little bit surprising. So, we want to see about sea level and really ask why would that matter in a consideration of an energetic Earth. And really, what the underlying theme here, which goes to almost any of the energy processes that we could have considered in this course, is the surprising complexity that exists even in a fairly simple and fundamental idea. So, what's so important about this reference level, this thing called sea level? It actually holds rather surprising significance in this unexpected complexity. I think from the time we're young, we probably learn that we reference elevations relative to this thing called sea level. If we're more precise, we will sometimes call it mean sea level, which actually plays a big role, but then raises the statistical question of how we actually do that averaging. It turns out that's not as easy as we would think. So we think of a beach that's got a maximum elevation of 10 meters above sea level, or a mountain of reasonable height of 3,300 meters above sea level, and we use those reference terms all the time. And if you think about that, you might actually think that this is one of the most stable and simple and abiding values that we can imagine. And it turns out that that's not the case. It's actually surprisingly complex. In fact, it's not even sea level, isn't even a fixed distance from the center of the Earth. Because the Earth rotates, there tends to be an equatorial bulge, and that influences the way we think about sea level, which is a key concept as well. And all of these concepts that we're going to talk about in some way connect to the fact that the Earth is an energetic place. And so if you thought that the idea is simple, you've missed a lot. And what we want to do is just have some fun near the end of this course and point out some of these connections. So what is so energetic about sea level? What are the energetic processes that seem to change the apparent amount of water in the sea, or the level at which we measure sea level elevations? And what we want to provide here is a quick overview and use that as an excuse for a review of that question, or the answer to that question, in 3 parts. And sort of the basic outline is that there's a number of influences that certainly play a minor role with respect to the determination of sea level in the system. That they don't dominate, but if we take account for those and we plan for their influence, we can easily accommodate them. Some energetic influences play a rather dramatic but local role, and we'll see some of those, and we've already seen some, and we'll recap that. And a few of these are really important influences, and one in particular that plays this crucial global role. And first category here, these local influences, of course, that many important things are happening at this interface between ocean and air, or between ocean, land, and air. That exchange surface or interchange surface plays an enormous role. First of all, of course, that the ocean is continually receiving solar radiation. It's a solar collector, and therefore it's continuously causing evaporation to take place. And it's sometimes having the reverse effect of that, which is that it gets rained on. And when this happens, obviously there's a loss of water and level that's fairly inconsequential associated with that evaporation. And again, where there's rainfall, and of course that quickly is smoothed out by the process of gravity and wave propagation. But it's also a surface on which numerous and valuable gases are exchanged. That the ocean is this phenomenally important reservoir. It's a reservoir for greenhouse gases, particularly carbon dioxide, but it's also a reservoir for a variety of other gases that are dissolved within it, like nitrogen and carbon dioxide that we mentioned, which plays a role in life as well as the global climate system, and oxygen. Almost everything is dissolved in water, at least to some extent. And of course we sometimes have other phase changes, particularly freezing and sometimes melting, and we get the formation of ice at the polar elevations or latitudes, and we have the melting of that takes place when an iceberg, say, drifts into an area of warmer water. Even if we see a tranquil ocean that seems relatively inactive, these exchange processes are taking place pretty well continuously. The sea surface at its base level of the global hydrologic system is really the staging ground for all sorts of dramatic things, of storms and floods and hurricanes and tornadoes. In fact, I think that that view of the staging ground is really important. I'm not sure if you've ever visited a major theater when it's got a play on and compared that to visiting when it doesn't have a play on. A stage is a pretty sterile place. It's a pretty flat place. It's a pretty uninteresting place. But what's important about the stage is not its physical attributes, although those are important. But what's really important, of course, is what takes place upon it. That the physical attributes are really a supporting structure for this dramatic encounter between personalities and events and circumstances that make for a great play. And really we think of this sea level as being a staging ground for a great play that involves the famous and energetic actors of hurricanes and tornadoes and storms and tsunamis that are created as part of that original foundation, that stage itself. Some of these dramatic local effects, of course, relate to something really crucial, which is, of course, that the ocean surface is almost never completely flat, but almost always has a sequence of waves upon it. The sea surface must consider these waves if we're going to be serious about it. And what we typically do historically is we divide those flavors that the waves come into three basic categories. There are waves that are induced directly from the wind. So these are the wind-induced waves, which are really derived solar energy, as we'll remind you of in just a moment. There's waves that originate from gravity that really has got to do with the attraction of the Earth to the Moon and the Sun and the way that differentially influences the oceans compared to the center of mass for the Earth, and of course a bunch of waves that are generated by local motions of the Earth that includes things like volcanoes and earthquakes and even things like landslides or a major slough of ice or a rockfall or an asteroid impact. Let's think about wind-induced waves for just a minute. These wind-induced waves are found near the end of this long energy cascade. A quick reminder that pressure differentials are caused by differential heating that take place because of surface differences or differences in orientation or differences in latitude, differences in season. And these pressure differentials between areas of latitude in particular or between land and sea produce a circulation. And the circulation, of course, causes the ocean to move and the atmosphere to move, and that transports heat polarward. And in the middle latitudes we get this derived activity or eddy motion typically associated with the atmospheric transport processes. But all of this stuff is going to be acting on the surface of the ocean, and all of these things tend to produce wind systems, upwelling, downwelling, thermohaline circulation system, and the waves on the surface are caused by the action of these events that produce typically this typical characteristic motion associated with that friction at the surface. These are waves in New Zealand in this particular picture that are just rolling in, can be extraordinarily picturesque and relaxing. And this is typically a picture of wind-induced waves, where the ocean waves are most commonly caused by the wind, or at least the ones we characteristically think. The tide is certainly continuous, but we often don't think of the tide as a wave in the normal sense. We think of that as sort of an undulation in a larger period sense or a lower frequency. The wind influences the waves primarily in three ways: by the larger the wind speed, the larger the waves; the longer the wind duration, the larger the waves; and typically the larger the distance over which the wind acts, which is a concept called fetch. We get larger waves as well. And these waves come in a variety of kinds that we distinguish. That we have ripples, which sort of instantly die down. They're really surface tension and gravity effects. We get swell waves, which are typically organized waves that happen when there's persistent winds that really allow the ocean to become organized in the surface, and we get long and regular pulsations of undulations of water surface. And then we get our sort of more characteristic or typical waves, which are typically steeper and less wide than a swell. They're typically more disorganized. The swell is usually a fairly coherent structure. Here's a typical situation where we have a wave with its characteristic breaking as it appears to the shore, often stormy, often dramatic, sometimes dangerous, sometimes extraordinarily attractive. If you have to be a surfer, happen to be a surfer, and are drawn to this kind of energetic exchange, which is harnessed or at least in some way tamed by a surfboard or as it rides that particular energetic system towards the shore. The typical characteristic of these very regular waves that are characteristic of swell, where they've organized themselves into quite steady and uniform trains. This typically is characteristic of a pattern of disturbance that happened a long way from shore, and the separation of those frequencies, almost like the separation of the colors in a rainbow, take place over long distances under the right conditions. And of course, these waves can be dramatic. These large waves, when they impinge on the coast, can produce dramatic effects and can cause destruction, can wreck ships and rearrange harbors, make travel extraordinarily difficult. But what we have also here, of course, are incredibly important exchange processes where salt and water, where evaporation and carbon dioxide exchange, where aeration, where all sorts of important exchange processes are taking place across this highly turbulent surface. This often produces quite very conducive systems to very rich biological systems where we get growth of mussels and clams and shells and a variety of organisms that can live in this wave-swept area of the land surface. The water that's brought in by the waves actually has to get out again, and this actually creates another phenomenon that we'll just mention in passing, and that as the water flows in, brought in by the breaking waves, there's a net flow towards the shore. In order to balance this so that the ocean doesn't empty itself, there is a net flow out, and sometimes you can see the effect of this net flow out as a kind of a differentiation in the structure of the waves. We see sort of a attenuation. This is an organized outflow, which is called a rip current or a rip tide, taking place with the net flow balance that has to take place with the water that's coming in with a wave will go out. It turns out that those things organize themselves again into fairly coherent structures, even as the swell does. And what the ocean is constantly doing is that fascinating process of gathering things together and spreading them out again, a process of collection and dispersal. And that's very characteristic of wave actions. We have not only waves in the normal sense, but we have tides as well. There is a tide in the affairs of men, Shakespeare says in Julius Caesar. And the idea of that variation, that situation where you've got high water, where ships can leave a harbor safely, and you've got low water. This is characteristic of a receding tide here, where we've got this flat beach and the tide going out, and things are exposed, and you can view life and poke along the shore and have a great deal of enjoyment as a result of the variation in tidal structure. Tides occur, as we haven't really studied in this course, but most of you probably know, primarily as a result of a differential gravitational pull, another geometric effect, where the sun plays a role too in terms of its own geometry and causes this regular rise and fall in sea level, accompanied by many horizontal flows that are taking place throughout the entire Earth as the Earth, in a sense, turns under these gravitational influences. And because of the moon and the sun and their coordination, moon phase turns out to play a significant role in creating the intensity of these waves. And the effect of these happens everywhere in the ocean, but the effects are sort of accentuated or made more noticeable by the coasts, and we get a more obvious occurrence at that point. And what all of our studies show is that as simple as these same things are to explain on the basis of simple geometry and gravity, their actual manifestations are enormously complex, where we get very important secondary effects that have interactions with coastlines and tidal influences that resonate in different structures, producing a very complex overall pattern. Here's the basic structure. Of course, the moon attracts the water, and since the oceans near the moon are attracted the most, then we get a high bulge that follows the apparent position of the moon. The center of the Earth is closer to the moon than the far side, so it tends to move a little bit to the left, and we end up with this rather elliptical shaped ocean, and the Earth turning underneath that, which produces a variation between low tides at the poles, another geometric influence, and high tides at this effective equator, that is not the true geometric equator, but the equator that is directly opposite the moon. And when the sun and the moon are aligned, we tend to get particularly high tides. When the sun and the moon are in opposition, they're pulling the Earth and the oceans in different ways, we get the much lower tides. We call these typically spring tides, and these typically are the neap tides, and we get that variation. Under quarter moon circumstances, sometimes the tides go to almost no level and no variation at all. But we get these dramatic effects. One of the most amazing is in the Bay of Fundy in Canada, where the tidal variations are huge and dramatic, and of course get humans to look at them and say, I wonder if we could harvest these. And there are many challenges associated with doing that. But here's another location where we've got a huge variation between the low tide situation with the water receded and the high tide situation, another wave action of other significance. The other complications, of course, that relate to this are the fact that the Earth's got a complex distribution of mass, or land mass, and these land masses act as an obstacle, and they change the direction and speed of both waves and currents, and that's responsible for the formation of these gyres that take place. And with gyres we have mounds, the deflection of current, and we have another variation in sea level that takes place as a result of this overall circulation system, where we get mounds of water. We've also learned that in terms of our ENSO system, our El Nino Southern Oscillation System, that we have a basin-wide tilt that's formed most characteristically across the Pacific, where the western edge tends to be in a little bit higher elevation than the eastern edge because of the cumulative effect of that equatorial current and because of the influence of the shear force of the wind that blows across the equator and produces that Walker cell that we've learned about that changes. Because everything's dynamic, there's a sloshing set of motions, sometimes called satiating motion, where you get a variation in level that's sort of equivalent. If you were to take water in a pan and give it a shake, it would slosh back and forth between two different sides. The ocean does this kind of thing as well. And of course, we've learned that we get storm surges associated with winds and currents, and this Ekman process, which tends to impel water to run up a coast in a way that it wouldn't do it without this Coriolis effect generated by wind and by current. And of course, we get movement induced by changes in the land surface, and we'll look at these in just a minute. And we get major potential for changes if an ice sheet were to slide. And one wonders what tsunami or what effect would be created if a major ice sheet off Antarctica or Greenland were to become unstable and slide into the ocean with a massive coastal and land associated or solid surface associated disturbance. So these waves produce shock, and they sometimes have, from a human perspective, shocking consequences. We end up with tsunamis and other dramatic encounters, and these can be caused by a variety of different means. Submarine earthquakes, where we got convergent plate boundaries, and the subsurface, the bottom of the ocean shifts dramatically and throws the ocean into motion. Volcanic activity, hot spots of the mantle can release magma and cause the fairly rapid and sometimes amazing growth of islands. We can have landslides that take place, typically near coastal areas, that cause local sloshing and effects. Meteorite impacts can produce enormous tsunami-type waves. If there's an impact in the ocean, that creates a disturbance all over the place. And of course, explosions, and particularly those that might be induced by humans, either accidentally or planned, when we're experimenting with the kinds of forces that we're now able to unleash. And the water in these cases will suddenly change its elevation, and it will create a disturbance which radiates outward from that location. But the speed at which these waves travel through the open ocean can be absolutely tremendous, almost at the speed more characteristic of an airplane than any other form of human transit, where we've got speeds that are very typically in the neighborhood of 500 to 800 kilometers per hour. So the moral of this is that you need a head start or you're never going to outrun a tsunami wave. And this, of course, creates a whole network of monitoring systems where we've tried to get advance notice of the potential tsunami waves by having very accurate wave or water surface measurement devices that are trying to represent this coherent large-scale structure associated with a tsunami, so that we can give people a chance to escape from the shores and at least save lives, even though we typically can't move our human structures nearly as quickly as that. And there's been recent examples. This is actually a seawall that is being inundated. The tsunami that was generated was far in excess of the design values. And that happened in Japan in a big way, of course. Just in the 2011 tsunami that was generated by those massive earthquakes off the coast of Japan. We live on a tectonically active planet, which creates enormous challenges, but of course is part of the secret of why this planet is habitable to begin with. Another example of a tsunami wave which is coming in, and these play tremendous havoc, of course, with the kinds of structures that humans build. We are able to build structures that are more able to withstand this kind of assault, but only at great cost, and there's huge economic penalties associated with that level of construction, as well as environmental ones. And so one of the realities is that we are vulnerable to our energetic Earth. It has moods and characteristics and capacities which are far in excess of what we can economically manage as humans. And in the end, the last thing perhaps of most profound global significance is that we live in a world which we believe is warming. And those warming effects are very likely associated with human activity. It seems a very inescapable effect that humans are not only able to live on the surface of the earth, but we're influencing it in a great many and profound ways, even to the extent of influencing our climate system and the weather systems and even ocean chemistry. And as the water warms, one of the things that's characteristic about warming water, including ocean water, is warmer water will expand. And if the oceans become warmer, they will occupy a greater volume, and sea level will inevitably rise. And so that means that subtle changes in the ocean level may be the best integrated measure that humans have for the shift in the average temperature of the Earth, that we can begin to observe those things. And to me, the image that I want to leave you with is this image of a bird that's enjoying the coastline, that's unlike humans, not able to reflect on the nature of its existence in the same sense. And for me, this energetic planet which we enjoy and live on is a place that should be enjoyed, it should be pondered, it should be respected, and to a very large extent celebrated. It certainly should be experienced. We should integrate those things together, but I think we also have an obligation as intelligent human beings and caring human beings to be good stewards of this amazing planet that we get to share.